All right, so as we go ahead and get ready to do the follow-up video, so I am looking for a couple of things. One, choosing the best indicator, a buffer problem, each type of titration, but I think we just had the strong one left, and buffer capacity. So I'm going to do buffers first. So first of all, when we talk about buffers, what we are talking about is something that automatically has a both a weak acid and its conjugate base in solution. So by definition, a buffer has to have both of these components in them. So a lot of times you see things that are conjugate acid-base pairs together. So something like ammonia with the ammonium ion in it together, those two things together are a buffer. Trying to talk about something, we could even use HF and the fluoride ion as a buffer system. So anything where we have both as a weak species and its conjugate can be a buffer. Now, when I say it can be a buffer, there's an equation that we typically use called the Henderson-Hasselbalch equation. And with this equation, part of the buffer is the fact that this ratio of the weak species to its conjugate has to be within a factor of 10 of each other. So that means that either my base could be 1 and my acid could be 10, or I could have this flipped and I could say that my acid is 1 and my base is 10. If we actually plug in those values into the logarithm, what we actually get is we get pH is equal to pKa either +1 in the case of 10, or we get pH is equal to pKa -1. And that's actually where the notion of pH should be equal to the pKa plus or minus 1 comes from. The reason why we pick this factor of 10 is because we want the buffer to resist changes in pH for either adding an acid or adding a base. So we basically have this general rule where we're like, well, as long as we have them within this range, the buffer should work, the buffer should function. I should be able to add either acid or base, and I should have enough of the weak species to combat both of them, either one of them. So this is what we use. This is how we get there. So because of this notion of pH is equal to pKa plus or minus 1, when we're therefore trying to choose a buffer system, that's what we're looking for, is that plus or minus 1 idea. So when we are trying to choose a buffer, let me go ahead and grab a little, there we go. So when we're trying to choose a buffer system, if let's say I wanted something that was going to be, the goal is say a pH of 4, then I'm looking for something in the 4 range. So these are close to 4, and then I want whichever one is closer. So basically 4 minus 4.19 is 0.19, 4 minus 3.77 is 0.23, and this one is closer. This difference is less, so therefore I would use this as my buffer system, which means I would want both the C6H5COOH, and this is an acid. I know because of the COOH, I would also want its conjugate base, H5COO minus, for my buffer system. So let's actually go ahead and finish out this problem. Since I have a goal pH and I have that, let's actually ask what then ratio would I need? So if I have my pH is equal to pKa plus the log of AHA, A minus over HA, what I can then do is my goal pH is 4. That's what I had over here. And I'm just going to use the pKa out of the table. So 4 is equal to 4.19 plus the log of A minus over HA. We actually already did that subtraction. Negative 0.19 because I subtracted 4.19 from both sides is equal to the log of A minus over HA. One thing that I should be able to note here is that because my pH is lower than my pKa, here my pH, no, there we go. My pH is less than my pKa value. I'm going to need more HA. I'm going to need more of the acid because I'm going to be close in that ratio. But if I had an equal amount, I would be at my pKa. I want less than my pKa value. To get a lower pH, I need more acid. So when I get this ratio back, that should be what happens. This is then 10 to just a negative 0.19. So whatever that number is, raised to that is going to be equal to my ratio. For those people wondering why this video is slightly late, it's because I wanted to like prepare, and then I realized that I was not going to have time to prepare, so I am actually winging this because that's the only way I was going to get this done. So there's my ratio, except that this isn't a ratio because it's only one number. So we're going to employ a tool left over from algebra where anything over 1 is the same number. So here, what I can now say is that my ratio of base to acid is 0.65 to 1. And what you should notice here is that my acid value is larger. So the 1 is for the acid, the 0.6 is for the base. And we predicted that because my desired pH is lower than my pKa, I should have more acid. And that is what is predicted here. So this is an example of a buffer problem. But I know that the folks that want to talk about buffers, this is not the kind of buffer problem that you meant. Don't worry, I know. But I did want to, still don't think I wanted. Let me double check. Oh, buffer capacity. That's the other thing we need to talk about, buffer capacity. So when we talk about the word capacity, so realize that there's a lot of ways to talk about capacity in the real world in the English language. Capacity in the English language basically means how much can it hold? How much can something hold? So in my class, I was using something like elevators or rooms. So we will sometimes talk about a room capacity. And the room capacity means how many people can you take? How many people? How many human beings? How many people can be in that room? So buffer capacity is going to be related to this idea. So buffer capacity is essentially things like how much acid or base can be resisted by the buffer, resisted by the buffer. Essentially, we want that buffer to be able to still work. So the thing is that this is usually done by talking about things to make my writing go faster. I'm just going to use HF and F minus. But if I had this ratio and I told you like, so I've got a couple of options for my buffer. I've got a 0.1 molar of each, or I have a 0.5 molar of each. Which is the larger capacity? Which buffer has greater capacity? I want the bigger number because the more of those conjugate species that I have, the more it's going to be able to react with additional acid or base added into it. So basically, the higher the molarity of buffer, the greater the capacity. So that's what you're usually looking for when we're asking about buffer capacity. You're looking for the molarity of the buffer itself. Do one more buffer problem. I need to use something where I have the pKa. Hey, look, I can use HF because it's in there. Fabulous. A buffer containing, we're just going to make our math easy, 1 molar of HF and 0.1 molar NaF. Has, sorry, 100 milliliters of this buffer. This is not very good English writing, I apologize. This is the reason why when we write exams, it goes through a couple of people so that my syntax can be edited. What is the pH after 10 milliliters of a 0.2 molar sodium hydroxide solution is added? And we'll go ahead and just give the pKa of the buffer because I'm going to nab it out of this table. It should be either the Ka value or the pKa value should be part of the problem. And I am just using the table that I had. pKa of HF. So one of the things with these problems is you actually have a lot of different species to take care of here. We have a weak acid, we have a weak base, technically a salts, and we've got a strong base. So there are 3 different species that are all hanging out together in the beaker, and we want to know what happens to them. Just like a titration, the first thing we're going to do is react the strong species. So this is true when you're doing weak acid, strong base titrations. This is true when we're doing weak base, strong acid titrations. It's actually still true when we do strong titrations. But we react the strong species. So only one of those 3 things I highlighted is strong. That's the sodium hydroxide. I'm going to go ahead and get rid of the sodium ion because that's a spectator ion. We don't need it. Bases react with acids. So we know that bases react with acids. So the next thing I'm going to have this react with is the HF, is that weak acid, because the strong base will react with the weak acid. Acids react with bases, bases react with acids. That's then going to form my conjugate species. I again got rid of the spectator ion, I got rid of the sodium. If you guys want to see it, we can put it off to the side, but it's not going to affect the pH, so I've left it out here. So this is the reaction I then care about. To make it balanced, we can go ahead and put water, but it's a liquid, we're not going to calculate that either. So since I'm reacting the strong species, this means I have to do this in moles. So I am reacting, reactions happen in moles. So I said I had 0.1 molar and 100 milliliters. So that gives me 0.01 moles of HF and the same of my F minus, because I have the same amount. So all I did there was I took my molarity and multiplied it by my volume for those. Then we do the same thing for my strong base. I have 0.2 molar times 0.01. So I have 0.002. Now that I have my reaction, I'm going to do my subtraction. I'm going to subtract the smallest number, just like in a titration problem. But we add on the other side because here's my arrow. So therefore, on the other side, I have addition instead of subtraction, just like equilibrium. And see what we get. 0, 0.008, 0.012. So perhaps when we think about this, I added a base, and when we were done, I actually now have more base than acid. So when I go ahead and go to my Henderson-Hasselbalch equation, I can just plug in these moles. I don't actually have to change things back to molarity. God, I'll give myself a pKa. I was so nice to me. 3.15 plus 0.012 divided by 0.008. Log. Don't forget the log. So I get 3.15 plus 0.176. My pH is equal to 3.33. Rounded. Some things. So again, usually most folks have issues setting everything up in the beginning. So typically the beginning portion where we were trying to figure out what things react with what is usually the difficult part because you have to come up with the equation on your own. So my recommendation is to focus on the strong species because the strong species has to react in moles, and that's going to be your first step. So that's what you should look for and focus on. Then from there, the other thing is that you can go back to molarity for this ratio, but you don't have to. For those of you that haven't seen it before, so when we're doing this, this is basically the moles of A minus divided by liters of solution divided by the moles. This is molarity, right? Molarity of the acid divided by liters of solution. Those liters would be the same because everything's happening in one beaker. Everything's happening in the same thing. So if I did go back to molarity, I would be dividing both moles by the same number. Well, when you divide both by the same number, when you divide fractions, dividing fractions, I forgot what grade this was, but when I learned how to divide fractions, my teacher was Mr. Button, and he would tell me that dividing fractions is as easy as pi. You flip the second number and multiply. So there's my redoing of my dividing fractions, flipping the second number, multiplying. I'm going to go ahead then and cross out like terms. Those are my liters of solution, and I end up with my moles of my A minus divided by my moles of HA, which is essentially what I used. So you can use molarity in the Henderson-Hasselbalch equation, but you can also use moles as long as it's the same. As long as either both numbers are molarity or both numbers are moles, as long as they're the same unit, you can use either one. So let me check my list because I lost track of where I was. I meant to write it. Oh, I did write it down. I wrote it down over there. Okay, we did buffer capacity. We did buffer problems. I've got indicator left over, and I have a strong titration. So, this was the one I meant to grab something for because I don't like what I have in the notes. So I'm going to grab what I do have in the notes, even though I don't like it, and I'll show you why I don't like it. So this is the thing that's in the notes for best indicator. This automatically gives you a pH range. So the thing is that that's not what we do on exams. So what we do on exams is we give you usually a PI, which really is actually the pKa of the indicator. So sometimes that's what it is. Depending on the textbook, some textbooks don't like to call that a pKa because we already are using pKa. Newsflash, indicators change color in acids and bases because they're losing or gaining a proton. If they gain or lose a proton, they are acids or bases. So typically what this works, and so I'm going to make these up because I didn't prepare like I meant to prepare. This could be 1.5 and this could be 4. I'm going to do round numbers to make my life easier. This could be 4. Actually, it would be something like, we don't care. Dr. Taylor, just keep going. 5.0, 5.2, 6.8, 8.1, 9. So we would not give you these ranges. We would instead give you either a PI value or or a pKa of the indicator. We do sometimes just call them pKa's because that is what they are. So then when you're choosing an indicator, there's two other pieces of information that we need. One, we want to know what the expected pH of the equivalence point is, because we would like the pKa of the indicator within plus or minus 1 of the equivalence point, because we want the pH to change where we care, and we usually want to look to know where the equivalence point is. So we want an indicator that's going to change near the equivalence point. The other thing, though, that we also usually want is, if possible, we want it to go to go with a color to colorless, or vice versa. But we want that sort of a transition. So we're going to do two examples using the information I have. In one of them, I'm going to say that my equivalence point is 5. So this is going to be A. So we're going to do this one first. So if I have an equivalence point of 5, then I want something that's plus or minus 1 around 5. So I've got kind of like this range in here. So any of these 4 would technically work. Since I said that the pH of my equivalence point is 5, and I actually have an indicator whose pKa is 5, then this is going to be the best one. But what you should notice is, as we're looking at all of these transitions in here, all of these transitions are colors. And really, the yellow to bluish purple might actually be easier to see. Oh God, orange to yellow sounds awful. Red to yellow and yellow to red also sound awful. But these are all color changes, and those are my only options. So since these are all color changes, I'm just going to go with the one that's closest to the thing that I want, which is the methyl red. So everything is a color. I'm going to pick methyl red. Next option. Next example. Equivalence point is 8.5. So if my equivalence point is 8.5, I'm going to use a different color. We're going to use a highlighter. Use pink. So if my equivalence point is 8.5, I'm getting towards the bottom. These two both look good. Technically, the 8.1 is closer. But here's now where I want to go ahead and look at my options. And my options have either a yellow to red transition or a colorless to reddish pink. This colorless to reddish pink is going to be much easier to actually see. So even though the chrysal red is a little closer to the range I'm looking for, this phenolphthalein is going to be much easier to use. And therefore, my human accuracy, the fact that I am going to look at it with my eyeball, is going to be more accurate with the phenolphthalein. So even though a textbook may be like, well, the chrysal red is closer, guess what? Your human eyeball is going to have a heck of a time trying to look at the difference between yellow and red. Whereas the human eyeball, much better with colorless to reddish pink. So the phenolphthalein is going to be your best option for this, even though it's not actually the closest one to that point. Notice it's still in range. So it is still in that like plus or minus 1 range. So it's not a bad option. But it's better because of that colorless to color. Buffer capacity, buffer problem, best indicator, strong titration. Last thing. We're just going to go ahead and do this from scratch. What is the pH of a solution after, I can't spell the word solution. Make it big. of a 0.25 molar NaOH solution after, oh no, we should make this weirder. I don't know. Barium hydroxide solution after pH of a 100 milliliter 0.25 molar barium hydroxide solution after numbers 150 milliliters of HNO3 is added. Trying to do things that are not just sodium hydroxide and hydrochloric acid. So there should be a question mark there. So first, we got stuff to do. We're going to react the strong species. Strong, react. Everything is strong. The acid is strong. The base is strong. Now, in order to make this work, what I can go ahead and put in my barium hydroxide plus my HNO3. But these are both strong species. So what's going to serve me better is to use a net ionic equation. And really all I'm going to care about there is I'm going to care about the things that are going to be in my solution that might affect my pH. They're going to be the things that are things I can't cancel out on both sides, things that are always soluble. This is back to chapter 9 and Gen Chem 1. So because of that, I can think about the ionic equation, barium plus 2 hydroxides plus a proton plus NO3 minus would yield the barium would still hang out plus water plus the NO3. So from all of this, I'm going to get rid of whatever is the same on both sides. That's the bariums and the nitrates. So the only things I have left is my waters plus my protons. Oh, this doesn't balance. So I can fix this in a couple of different ways. What I am going to do is I'm actually going to get rid of that so it balances. But that too is important. So even though for my net ionic, I'm just going to make things balance and make it go away. What I do need to keep in mind is that this 0.25 molar of barium hydroxide means that for every 1 barium hydroxide, I actually have 2 hydroxides. So I actually have 0.5 molar hydroxide in that solution. So then when it comes time to multiplying times my volume, I have 0.05 molar hydroxide because I have 2 hydroxides for every 1 barium hydroxide. So we can't just ignore the stoichiometry. What I'm going to do is I'm going to multiply my hydroxides by 2 because that's how many hydroxides are coming to the party. 0.05 moles, because I'm reacting in moles. HNO3, I didn't give myself a molarity. 0.1 molar. Sorry, that should have been the problem. Just add it, 0.1 molar. Now that weird question mark's hanging out. Sorry, should have been the problem. So 150 milliliters times 0.1 gets me 0.015 moles of my H plus. We're going to subtract the smaller number. That gets rid of all of my acids. I have some amount of base left over. Now, the thing is that this again is moles of OH minus. The lovely thing here is since the goal is pH, I can still use this. So keep in mind that since I did add those two together, I do have to change my volume. So I have 150 milliliters sorry, 100 milliliters and 150 milliliters. So 100 plus 150 is 250 milliliters or 0.25 liters. So 0.035 moles OH minus divided by 0.25 liters is 0.14 molar OH. The pOH is equal to negative log of 0.14. The pOH is really small, 8539. The pH is 14 minus the pOH. pH is equal to, something should be pretty high, 13.15. And when we think about that, realize that what was happening is, assuming that barium hydroxide was the thing in the beaker, we added some of the acid, but that didn't get us very far. So what we had left over in the beaker was that hydroxide, or that barium hydroxide. And so we should have expected, since base is what was left and strong base was what was left, that pH greater than 7. Those are the questions I think we had left. So I'm going to go ahead and stop the recording.